So the last application that we're going to look at is logic circuits. So logic circuits is contained in Rosen section 1.2.6. And logic circuits have applications in both hardware design as well as in theoretical computer science. So you might have heard of ASICs, or application-specific integrated circuits, or FPGAs, which are field programmable gate arrays, which are both devices that are designed for very specific purposes by using user-specified logic circuits and logic gates to be able to more efficiently perform some sort of computation rather than a CPU, which is designed for more general purpose computing. So logical circuits can help you to design FPGAs and ASICs, but not only design hardware, but it's also applicable to theoretical computer science. So as you will learn in Computer Science 465, logic circuits come into play when you try to prove results about different complexity classes. So for example, when you're comparing P versus NP complete and various things like this, logic circuits are fundamental in the analysis of theoretical computer science. So logic circuits, very good application of propositional logic, both for hardware design as well as theoretical computer science. So what are logic circuits? So the first thing we got to do is define what a logic gate is. So we have different sort of logical operators. We have not, we have and, we have or, we have implication. But we recall that we can relate implication back to ors and nots. And we have by implication, and we know that we can relate that back to ands, nots, and ors. So really, we only really need 3 logic gates. And so let's go ahead and introduce our different logic gates. So these logic gates are a diagrammatic representation of the different logical operators that we have seen so far. So here, our very first one is an inverter. This right here is a diagrammatic representation of a not. So it takes your propositional variable and it applies a not to it. We have another one, which is going to be and this right here is going to be our diagrammatic representation of an OR gate. So it takes 2 of our propositional variables right here and it combines them into an OR. And our very last logic gate is going to be an AND. And that right there is a diagrammatic representation of an AND gate right there. And so using these diagrams right here, we can represent different compound logical expressions. And usually the way that you would call that is a combinatorial circuit diagram. So here, what I've written is that a combinatorial circuit is going to give us a diagrammatic representation of a compound expression using those sorts of diagrams that we are given right here. So let's go ahead and try to figure out a few examples of this. So, for example, we could try to figure out what is the combinatorial circuit for implication. So if you wanted to look at P implies Q, how could we write a combinatorial circuit to give us a diagrammatic representation of this particular compound expression right here? Well, we already know that this thing is logically equivalent to the following statement. Not P or Q. Well, great. We have a not and we have an or gate. And we remember our precedence of operators, so we know this not applies to the P before we apply the Q right here. So if we wanted to give a diagrammatic representation of this, we could do it in the following way. We could write our couple of logical operators right here, and then the first thing that I'm going to do, because of my precedence of operators, is I'm going to invert this P right here. So it's going to go into an inverter or a NOT gate right here, and it is going to come out as a NOT P. And then after that, I want to use an OR gate, and I want to use an OR gate right there. And I want to use an OR gate with this particular Q. So I'm going to have to take this Q, and I'm going to have to stick everything inside an OR gate. So if I stuck it inside an OR gate, this would become not P or Q, which we know is logically equivalent to P implies Q right here. Fantastic. So that's one example of a combinatorial circuit of how you could represent a compound expression into a diagrammatic representation using this sort of circuit diagram right here. So let's see if we can't do another example, a little bit more complex. Let's see if we can't come up with a combinatorial circuit diagram for a compound expression that looks like the following. P if and only if Q or R right here. And notice that I'm using the brackets right here because our precedence of operators tells me that OR would be implied or applied before the biconditional would be. So I need these brackets right here to disambiguate this statement. I mean P if and only if Q or R right here. So I want to go ahead and come up with a circuit diagram or a combinatorial circuit to represent this compound expression right here. Well, thankfully, I know that this P if and only if Q right here, I know the definition of that. That's P implies Q and Q implies P. And I already have the circuit diagram for P implies Q right here. So what I'm going to do is I'm going to recall that this thing right here is logically equivalent, just the P if and only if Q part. That part is logically equivalent to P implies Q and Q implies P. So all I have to do is take this combinatorial circuit right here and copy it down a couple of times, once for the P implies Q and once for the Q implies P, and then combine them together with an AND operator or an AND gate. And I have that AND gate sitting right there. So let's go ahead and see if we can do that. So the first one I'm going to work on is this P implies Q. So thankfully I just have to take this and I have to copy it down as is. And I get P implies Q. Okay, that's fine. But then I need to combine it up with a Q implies P. Well, with a Q implies P, that's basically the same diagram right here, but all I need to do is reverse the roles of the P and Q because they're on other sides of this arrow right here. So in that case, well, I'm going to have to write another Q right here, and I'm going to have to write a P right there, and I'm going to have to do the same thing. I have my inverter gate. I have my OR gate. And I have my Q implies P. Great, so I have this expression right here as a combinatorial circuit. Well, not really. I only have the left-hand side and the right-hand side. I need to combine them up using an AND gate. So I'm going to have to take these two and combine them up with an AND gate. So I'm going to go ahead and stick for myself right here an AND gate. And there we go. I have my P implies Q and my Q implies P, which we know is completely logically equivalent to P if and only if Q right here. But then we also had this OR R right here. So we need to use an OR gate somewhere. So again, I need to use my propositional variable R right here, and I'm going to have to stick it in an OR gate. So here, I'm going to go ahead and write for myself another OR gate, and this guy is going to go straight inside, and then I'm going to take R or this expression right here, and what pops out the other side is P if and only if Q or R. And there we go. I now have for myself a circuit diagram, a diagrammatic representation of this compound expression right here. And as I said, this can help you in programming FPGAs and ASICs, but it's also applicable in theoretical computer science.